that I send this for. Okay. Representation theory by Kowalski. Okay. You can follow the contents of representation from this book. Okay, we begin from chapter 2, the language of representation theory. I established this definition for you. Let G be a group and K be a field. A linear representation of G defined over K is a group homomorphism such as rho from G to GLE of E. This definition and some properties for representation theory. Okay, E be vector space over a field K and GLE, the set of all functions from E to E such that F is linear and bijective. Then GLE with the composition operation is a group, and we see this. Now any homomorphism between two groups, okay, G and this group, is called a representation on G. The dimension of E is called the dimension of rho. So sometimes its degree or rank, the rank of this representation or the degree of this representation. Okay. Okay, and other properties and examples that you can follow from this book, and I express for you in the previous sessions. In these slides. We see all of these examples, okay? And also we have these two definitions. faithful and trivial representation of the group, and let K be a fit. A representation rho of G defined over K is faithful if rho is injective or one-to-one. Okay. On the other hand, the kernel of rho equal to the identity only. This fact is equal to that rho is a one-to-one or injective map. A representation rho of G on space E is trivial if rho of G equal to G, so that the kernel of rho equal to whole of G, because rho of all element equal to 1. Okay. Now we have some example. At the first we see this example in the previous session for a group G, for a group C, complex number with ordinary addition operation. We have the following representation: rho from G to GL of C, rho from C to GL of C, that we know that this is equal to the set of all non-zero one-to-one matrix by complex variation, and this is equal to C minus 0. By this function rule, rho of Z equal to e to the power of Z is a representation. Please note that GL of C equal to the set of all F from C to C, such that F is linear and bijective, linear and one-to-one. So that F belongs to this space if and only if there exists a non-zero complex number such as alpha F of X equal to alpha multiplied by X. We know this fact. Okay, so that we have this one-to-one corresponding F to this matrix or alpha. So we have this identification. Now we have this representation rho from C with plus two non-zero element in C with ordinary multiplication in complex number. This is multiplication in complex numbers. By this function rules, it is very trivial, that is a group homomorphism. Rho of Z1 plus Z2 equal to e to the power of equal to e to the power of Z1 multiplied by e to the power of Z2. But this is equal to rho of Z1 and this is equal to rho of Z2. So this is a group homomorphism and this is a representation. As another example, let G be equal to real numbers or complex numbers and S be an element of C. X e to the power of Sx. Representation Okay, this is this example. G equal to real number or complex number with ordinary addition operation. Then for each s in complex number, we have the following representation. This function from C to C minus 0, okay? By this function rule, for each x in our group G, Ks of x equal to e to the power of sx. This is a group homomorphism because Ks of x1 plus x2 equal to e to the power of s multiplied by x1 plus x2, and this is equal to this multiplication, and this is equal to this multiplication, so that this is a group homomorphism, because we consider in this group multiplication as binary operation, and in this group addition as binary operation. Okay, another example, let G equal to Z. Z is integer numbers. Then for any m in integer numbers, this map is a one-dimensional representation. Dear student, okay, thank you, Muhammad. For this example, for this group is a quotient group or quotient space. Okay, we have this binary operation for each two class or two cosets in this quotient space, such as x and y. The class of x plus the class of y equal to the class of x plus y. We know that x plus y is an element of R, and this is ordinary addition in real numbers. Okay, but this is the addition in quotient group, so that this is the natural definition for the binary operation of quotient of this group equal to the set of all equivalent classes or the set of all cosets x, such that x belong to, and also we know that this element or this cosets equal to x plus z, or the set of all x plus n, such that n belong to z. And also, if we define this relation in z for each x, in R for each x and y in real number, x has this relation with y if and only if x minus y belong to z, and this holds if and only if there exists an integer such as n such that x minus 1 equal to n. This must be belong to z. Okay. Then we see that the equivalent class of x by this relation, it's very trivial that this is an equivalent relation. On the other hand, this is antisymmetric and transitive. This class is the set of all y in R such that x have relation with y, and this is the set of all y such that there exists one integer numbers such as n such that this subtraction equal to n, and this is equal to this set. There exists an integer number such that y minus x equal to m, so that this y can be written by this form, x plus m, the set of all x plus m such that m belong to z, and this is x plus z. Okay, so that the element of this quotient group is the left cossets in z, or the set of all equivalent classes by this relation. For simply we write x instead of this class. Okay, in this quotient group, if we write x, we mean the class of x, and this class or the equivalence containing x. Now for each m in z, this representation em by this index from this group to the non-zero complex numbers by these function rules. For each element in this group, em of x equal to e to the power of 2 pi m x. Please note that this is a complex number and this is a non-zero complex number, so that this function is well defined. Okay, or simply for any x, we say that instead of this class, we always write for any x in this quotient group, the function rule of em equal to this. In our book, we see x mapped to this, but this is the class of x or the concept of x. Okay, it is very trivial that it is a group homomorphism, and so that em is a belong to this class, x must be in the relation with y, so that there exists an integer number such as n such that y equal to x plus n, so that e to the power of e 2 pi m y equal to e to the power of e pi m x plus n, because y equal to x plus n. And instead y we write x plus n, and this is equal to e to the power of this, and this is equal to this multiplication, but this is equal to the first only, because this is equal to 1. E to the power of 2 pi m n equal to 1. I write this for you. So very trivial, because e to the power of 2 pi m n equal to this order pair cosinus of 2 p m n 2 m n p and sinus of 2 m n p, and we know that this is equal to 1 and this is equal to 0. So that this equal to 1, and this shows that if we consider two equal in R divided by Z, EM of X equal to EM of Y. Okay, EM of X equal to EM of Y. Let me write this for you, that this is okay. This is EM of X equal to this, and this is EM of Y, and this is equal to EM of X, so that this EM is a group homomorphism, and so that this is a representation from this group. This is the proof of that EM is a homomorphism. EM of X multiplied by EM of Y. Okay, and also we have this example. Let Q be greater or equal 1, and Q is an integer number, so that Q must be equal to 1, 2, 3, 4 up to the n, and G be this quotient space. If the addition group of integers modulus Q, then for any n in this quotient space, this map is well defined, and it is a one-dimensional representation of G. Please note that all of these are one-dimensional. Okay, dimension for you. Let me recall this. Okay. Okay. Okay, let me recall again this the dimension of A is called the dimension of row or sometimes is degree or rank, so that the dimension of this representation is the dimension of this vector space. Okay, the dimension of this vector space. And we see that in this example all vectors. Okay, the non-zero element with the ordinary multiplying complex numbers. And also in this representation are in GL of C, and C is a one-dimensional vector space. Let G equal to this quotient space with binary operation. Then we know that this is a group, and the identity element of this group equal to this left coset, and this is the zero element of this quotient space. It's very trivial, because if we added 0, this equal to a class of n. Now let's assign to this quotient space and define row of this quotient space to non-zero complex numbers or GL of C by this function rules for each n. Row of to e to the power of 2 pi m n cube. This is well defined. Again, I prove that this function is well defined if these two are n minus n2 must be belong to QZ, this concept, so that there exists another integer number such as n3 such that the subtraction equal to q multiplied by n3. Okay, so that this is multiplication. Let me write better. This is n3 okay, so that there exists an integer numbers such that n1 equal to n2 plus q n3. So rho of n1 by this function rho equal to e to the power of 2 pi m n1 divided by q. So this is equal to e to the power of 2 pi m n2 plus q n3, because n1 equal to this, and this is equal to by this, and e to the power of 2 pi m n3 1. We see this in the previous example, so that this equal to the first item only, and this is equal to the item equal to this. This is equal to rho of n2. So that if n1, the class of n1 equal to the class of n2, then rho of n1 equal to rho of n2. And also it is very trivial that this rho is a group homomorphism, so that this rho is a representation. Okay, and now we have this morphism of representation. It is not that we know that the identity map is a I express this definition for you. Please group E be a vector space and F be a subspace of E for any representation of G such as rho. Let rho representation of G, rho from G to GL of E. We say that F is stable on the rho whenever for any G in G, rho of G of F be a subset of F, or for any X in F, rho of X belong to F, rho of G of X belong to F. then we say that F is a stable subset of E. Okay. Please note that for any G in G, row of G must be belong to GL of E, because we know that row is a group homomorphism from G to this group, GL of E. Okay. So G to GL of E, and GL of E set of all linear bijection operator from E to E. So that row of G is a function from E to E. So G belongs to G. Let me write for any G in row G of F is a subset of F. And so or therefore for any G in G, row G, the restriction of row of G in F is a function from F to F. By this inclusion, row G of F is a subset of F, so that we have this function. The restriction of row of G to F is a function. So if we define this restriction from G to GL of F by this function for any G in G, this restriction of G means this restriction row G restriction to F. We have a representation. Then this is a representation on G with the vector space F instead of E. The original representation is on E, GL of E, but this restriction is a representation with vector space F. This representation is called a sub-representation, and sometimes F is called a sub-representation of E. And this is a definition, the definition of sub-representation. Please note that again, for any G in G of F is a, because F is stable under row. No, let F be stable under row or invariant under row. Then the restriction of row in F and action of G on the from G to GL of E. We have the following representation: row tilde from G to D group GL of E divided by F. By this function rules, for any G in G, okay, for any G in G, rho tilde of G of X equal to the class of rho G of X. Please note that rho of X is an element of E, and so this is this equivalent class or this classes is an element of this, so that this is well defined for any X in E. Please note that this class and this class in this quotient space are equivalent classes in E with this relation. X have this relation with Y if and only if X minus E belong to F. So the class of X is this quotient X plus F. X plus F. And we have this representation rho tilde from G to GL of this quotient space. In our book, rho tilde of G of V is denoted by G dot V. Please note that we have this definition in the previous page. In our book, write G dot V instead of this. G in G, and for any class in this quotient space, this class is equal to V plus F. This is the left concept. G dot the class of V equal rho of G with rho of GV. There is no class of V1 equal to the class of V. This class minus this class, this subtraction, this is equal to this, and this is equal to 0 element in this space. So that this is a well defined representation. I write again this for you. This action is well defined. If V1 belong to this class, V1 this left concept, so that the subtraction of V1 and V must be an element of F, so that rho W, this W must belong to F, because representation is invariant F, since this is an element of F, rho G of F. But this is equal to rho G of V, and this is equal to this. by this equality. So that this is a well-defined representation, okay? And also let me okay. The definition, let G be a group and A be a field, a morphism or homomorphism between representation row 1 and row 2 of G, both define our car and acting on the vector space E1 and E2 respectively, is a car linear map. This is a linear map, okay, from E1 to E2 or vector spaces such that phi of row 1 of G V equal to row 2 of G of phi of V for all G in G and V in E1. One also says that phi in row 1 and row 2 or is an intervening operator, intervener between them, and one may denote this by phi from row 1 to row 2. This definition is ordered row 1 of G phi or row 1 of G equal to row 2 of G O phi. The composition of these two equal to the composition of these two functions. Let me find, okay, 4, 3. Okay, so that let me repeat this definition again. G be a group and K be a field, a morphism or homomorphism between representation row 1 and row 2 vector space E1 and E2, so that you can note that row 1 for example, row 1 is a representation from G to GL of E1, and rho 2 is a representation from G to GL of E2. Okay, then a homomorphism between rho 1 and rho 2 is a linear map from E1 to E2, such that we have this equality. This equality represents in diagram. Phi is a linear map from E1 to E2, and we know that for any G in G, rho 1 of G is an element of GL, is an element of E1 to E1, and for any G in G, rho 2 of G is a function from 2 to E2. Okay, rho 2 of G is a function from E2 to E2. Rho 1 of G is a function from E1 to E1. So this composition is well defined. Rho 2 of G O phi, rho 2 of G O phi, and also this composition phi of rho 1 of G. Okay, now in morphism on representations, we must have this equality for any V in E, rho 2 of G of phi of V must be equal to G of V, or equivalently phi O rho 1 of G for any in G, phi O rho 1 of G equal to rho 2 of G O phi. Okay, this equal to for any G in G, these equalities mean that for any V in E1, okay, phi of rho 1 of G of V must be equal to rho 2 of G of phi of v. And also note that we belong to E1, so that is a function from E1 to E2, okay? Since phi a function from E1 to E2, phi of v is an element of E2. Phi of v an element of E2, so that root 2 of phi can be act on this element of E2. Okay, and this is phi of phi. Now if we have this equalities or this equality, we say that is a homomorphism from row 1 to row 2. This is a homomorphism between representation, okay? And this is row from E1 to E2 is a homomorphism between row 1 and row 2 whenever we have these equalities, okay? We have these equalities. Okay, dear students, do have an operator theory. Okay, let me write this for you. Okay, thank you, and goodbye for now.